As we move deeper into our look at NMR spectroscopy, it's now time to talk a little bit about the origins of magnetism itself, and ultimately how we manipulate that magnetism to get the information that we want from our molecules when we do NMR spectroscopy. We first are going to talk about the various kinds of magnetism and where they come from. Now, admittedly, this is really a deep physics topic, and we're going to oversimplify matters by quite a bit because we're not going to dive into the grand quantitative detail of this topic, but we are going to definitely look at the basics. The key idea behind all magnetism is basically this: moving electric charges. Anytime you have electric charges moving, they will generate some type of magnetism. A classic example is simply a stream of electrons moving down a wire in an electric current. That will create a magnetic field around the wire, and I'll demonstrate that in just a moment, something called an electromagnet. Or you can have the electrons moving around the nucleus of an atom. That motion can create magnetism. Even an electron just sitting stationary, or even a proton or a neutron sitting stationary, can create magnetism as well, because all of these subatomic particles act as if they are spinning, and it's that motion that can create magnetism as well. We're going to demonstrate the electromagnetism for a moment using just a couple of basic components, simple components: a classic alligator clip wire, a battery, and a fairly powerful neodymium magnet. And in order to show this, I'm going to go to a close-up for a moment, which would be, of course, is never such a good idea. But here's the wire, classic alligator clip. And what I want you to see is if I take the neodymium magnet here, hold it up, not in front of myself, hold it up here and just push it near the wire. I want you to see, really, nothing happens. The plastic of the wire, the copper of the wire itself inside the plastic, neither of these are magnetic. But if I take the battery, and what I'm going to do is I'm going to touch the ends of the alligator clip to the battery, shorting the thing out and causing an electric current to flow through the wire, hold up my neodymium magnet to the wire, and you'll notice that they're now quite strongly attracted to each other. That flow of electrons running through the wire creates magnetism that the magnet can interact with. Now I'm going to set it down before the alligator clip heats up too much and starts burning my fingers. No sacrifice too great for my classes, but there is a limit. And I'm going to just basically take the thing again, and once again, now that the current is not flowing through there, the wire is non-magnetic again. So once again, it's simply the flow of electrons, the movement of the charged electrons through that wire that could create a magnetic field that you saw the magnet interacting with. Electromagnetism, we call it. Now, all subatomic particles also have the property that we mentioned previously: spin. They all act as if they are simply sitting there spinning on their axis, and that motion creates a magnetic field. The north and the south pole of a magnetic field as well. Electrons can do this, protons can do this, even neutrons. They are electrically neutral, but remember, they are built themselves from even smaller particles called quarks, and they have spin and electric charge. And so even neutrons can generate a magnetic field. The greatest example of spinning electrons generating a magnetic field is the magnetism found in any species with unpaired electrons in them. Now, almost all matter has electrons in it. That's a pretty common basic idea. But remember, the electrons are almost always paired. We even draw pretty little pictures showing, with little arrows pointing up and down to show the paired electrons in an orbital around an atom. We'll even make little more detailed diagrams showing the electrons spinning, one generating its north pole pointing in one direction, the other is north pole pointing in the opposite direction. We say the electrons are spin paired, and while each may create a magnetic field, it adds up to nothing. And so almost all matter we run across has all of its electrons paired up this way and is therefore non-magnetic. But we do run across once in a while species that have at least one unpaired electron and sometimes more. Free radicals, for example, generate a magnetic field. Or transition metals and sometimes lanthanide metals are also well known for having a number of unpaired electrons in them to generate magnetic fields. The classic iron magnet or this neodymium magnet, for example, has a large number of unpaired electrons in it that generate, each of them spinning, generating magnetic fields. In fact, to be honest, it is no coincidence that many of the classic magnetic metals that we find on the periodic table, iron or neodymium, samarium, tend to fall in the middle areas of the D block of the transition metals or in the middle of the F block in the lanthanide metals. That's where we tend to find metals with the greatest number of degenerate orbitals and unpaired electrons in those orbitals. Of the two types of magnetism that we've mentioned so far, the electromagnetism, electrons flowing down a wire, or permanent or fixed magnets, electrons spinning and their unpaired electrons spinning, generating magnetic fields, the electromagnetism can be the most powerful of the two, depending upon the amount of current that you're actually using. Neodymium magnets, iron magnets, and so forth can also be quite powerful. The third type of magnetism that we're going to look at briefly is the nuclear magnetism, the fact that the nuclear particles, protons and neutrons, also spin and can also generate magnetic fields. Now, one important point to remember about the nucleus is simply this: it's small. Atoms are not known for being terribly huge, but remember, compared to the size of an atom, the nucleus is orders of magnitude smaller yet. That means that the effects of the nucleus, as far as its magnetism are concerned, are going to be quite weak. It is the weakest of the three that we're looking at right now. Ironically, it is also the one that is most important when we do NMR spectroscopy. It is very weak, but it is detectable. We can manipulate it, and we can exploit it to get a lot of information about molecules that we might like to study.